Comets, those enigmatic celestial wanderers, have captivated humanity for millennia. These celestial bodies, often seen as harbingers of change or omens in ancient cultures, have a rich history in human mythology and science. From the ancient Chinese, who meticulously recorded their appearances, to the European Renaissance astronomers who began to understand their orbits, comets have always been a source of fascination and mystery. Often gracing our skies with their ethereal beauty, these cosmic travelers hold within their icy depths secrets to the early solar system. They are like time capsules, preserving the primordial materials from which our solar system was born. When we observe a comet, we are essentially looking back in time to an era when the sun and planets were still forming. But what exactly are comets, and why are they often referred to as dirty snowballs? The term dirty snowball was coined by astronomer Fred Whipple in the 1950s to describe their composition. This nickname, while somewhat whimsical, is quite accurate in describing the mixture of ices and dust that make up these fascinating objects. Imagine a cosmic refrigerator, a repository of remnants from the dawn of our solar system, frozen in time for billions of years. These remnants are composed of materials that were present in the early solar nebula, the cloud of gas and dust from which the sun and planets formed. By studying comets, scientists can gain insights into the conditions and processes that prevailed in the early solar system. Comets are precisely that: icy bodies composed of frozen gases, dust, and rocky debris. These materials are held together in a loose conglomerate, with the ices acting as a kind of glue. The most common ices found in comets are water ice, carbon dioxide ice, and carbon monoxide ice, but they can also contain more complex organic molecules. This composition, rich in volatile substances that would normally exist as gases at Earth's temperature, is why they are aptly nicknamed dirty snowballs. When a comet approaches the sun, the heat causes these volatile substances to sublimate, or turn directly from a solid to a gas, creating a glowing coma, and often a spectacular tail. Unlike the terrestrial planets like Earth or Mars, which are primarily composed of rock and metal, comets represent a time capsule from the solar system's frigid outer reaches. These regions, far from the sun, are cold enough to preserve ices that would otherwise vaporize. This makes comets invaluable to scientists studying the early solar system. Their composition, a mixture of ices like water, methane, and ammonia, along with dust and rock, provides invaluable clues to the conditions and materials present during the solar system's formation. By analyzing the isotopic ratios of these materials, scientists can learn about the processes that led to the formation of the sun and planets. As these icy wanderers journey closer to the sun, their volatile components begin to sublimate, transitioning directly from a solid to a gas, creating a visible atmosphere called a coma. The coma is a cloud of gas and dust that surrounds the nucleus of the comet, and it can grow to be thousands of kilometers across, and often a spectacular tail that can stretch for millions of kilometers. This tail is formed by the solar wind and radiation pressure pushing the gas and dust away from the comet's nucleus. The tail always points away from the sun, regardless of the direction the comet is traveling. This breathtaking display is one of the most awe-inspiring sights in the night sky, a reminder of the dynamic and ever-changing nature of our solar system. The celestial tapestry is woven with diverse objects, each tracing its unique path across the cosmos. From the twinkling stars that seem to stand still to the wandering planets and the elusive comets, the night sky is a dynamic and ever-changing panorama. Planets like Earth and Mars follow predictable, nearly circular orbits around the sun. These orbits are the result of the gravitational pull of the sun, which acts like a cosmic anchor, keeping the planets in a stable and orderly path. The predictability of planetary orbits allows astronomers to chart their positions with great accuracy, making it possible to forecast celestial events such as eclipses and planetary transits. Comets, on the other hand, are renowned for their eccentric and often highly elliptical orbits, setting them apart from the more orderly motion of their planetary counterparts. Unlike planets, comets can have orbits that take them far beyond the outer planets, into the distant reaches of the solar system, before they swing back close to the sun. This journey can take hundreds or even thousands of years, making each comet's appearance a rare and spectacular event. Imagine a racetrack where planets gracefully glide along the inner lanes, their paths predictable and stable. Each planet moves in harmony, following a well-defined route that ensures they never collide. This cosmic dance is a testament to the delicate balance of gravitational forces that govern our solar system. Comets, in contrast, would resemble daredevils, hurtling in from the outer edges, their orbits stretching far beyond the planetary tracks before looping around the sun and returning to the distant reaches of the solar system. These icy wanderers are like cosmic nomads, traveling vast distances and enduring extreme conditions as they journey through the solar system. Their highly elliptical orbits bring them close to the sun, where they heat up and develop their characteristic glowing comas and tails, before they retreat back into the cold, dark outer regions. This difference in orbital behavior stems from the distinct origins and gravitational influences that shape these celestial objects. While planets formed in the relatively stable and warm inner regions of the solar system, comets originated in the cold, distant outskirts. The gravitational interactions with giant planets like Jupiter and Saturn, as well as passing stars, can alter the orbits of comets, sending them on their long and elliptical journeys. Planets formed in the inner, warmer regions of the early solar system, where the sun's gravity shepherded them into more stable and circular orbits. These regions were rich in heavy elements and compounds that could withstand the intense heat, allowing planets to grow and develop into the rocky worlds we see today. The sun's gravitational pull ensured that these planets remained in a consistent and predictable path, creating a stable environment for the development of life. Comets, however, originated in the frigid outer realms, where gravitational interactions with giant planets and passing stars often nudged them into highly elliptical paths that swing them close to the sun before flinging them back to the solar system's distant fringes. These icy bodies are composed of volatile materials that vaporize when they approach the sun, creating the spectacular tails that we associate with comets. Their journeys are a testament to the dynamic and ever-changing nature of our solar system, where even the most distant objects can be influenced by the gravitational forces of the sun and planets. The cosmos is a stage for a celestial ballet, with gravity acting as the invisible choreographer dictating the movements of every object, from the smallest particles to the largest galaxies. This grand performance is a testament to the fundamental forces that govern our universe, creating a mesmerizing dance that has captivated human imagination for centuries. Comets, with their eccentric orbits, provide a captivating glimpse into the intricate dance of gravity in our solar system. These icy wanderers, often originating from the distant Oort Cloud or the Kuiper Belt, embark on long, elliptical journeys that bring them close to the sun and then fling them back into the outer reaches of the solar system. Imagine a celestial game of cosmic billiards where the sun's immense gravity acts as the cue ball, its influence extending far beyond the orbits of even the outermost planets. The gravitational pull of the sun is so powerful that it can capture comets from the farthest reaches of the solar system, drawing them into its gravitational embrace. Comets, like billiard balls scattered across the cosmic table, respond to this gravitational pull, their paths dictated by the sun's invisible hand. As they journey through space, their orbits can be altered by the gravitational forces of other celestial bodies they encounter along the way. As a comet ventures closer to the sun, its velocity increases, propelling it forward at astonishing speeds. The intense heat from the sun causes the comet's icy nucleus to sublimate, creating a glowing coma and a spectacular tail that can stretch for millions of kilometers. This gravitational tug-of-war between the sun's pull and the comet's inherent momentum shapes its elliptical path. The comet's journey is a delicate balance of forces, with gravity constantly pulling it inward while its momentum carries it forward. The comet swings around the sun, often at breathtaking speeds before being flung back towards the outer regions of the solar system, its trajectory determined by the delicate balance of gravitational forces. This slingshot effect can dramatically alter the comet's orbit, sending it on a new path that can take it far from the sun or bring it back for another close encounter. However, the sun's gravity is not the sole player in this cosmic ballet. The gravitational influence of other celestial objects, particularly the giant planets like Jupiter and Saturn, can significantly alter a comet's orbit. These massive planets act as gravitational gatekeepers, their immense gravity capable of capturing comets and redirecting their paths. The gravitational influence of these giant planets can send comets on entirely new trajectories, shortening their orbital periods, lengthening them, or even ejecting them from the solar system entirely. This dynamic interaction between comets and planets adds another layer of complexity to the gravitational choreography of our solar system. These gravitational nudges can send comets on entirely new trajectories, shortening their orbital periods, lengthening them, or even ejecting them from the solar system entirely. The interplay of gravitational forces creates a dynamic and ever-changing cosmic dance with comets as the wandering performers, their paths shaped by the invisible hands of gravity.